Well, so in this lecture, we will study direct methods of optimization of multivariate functions. Direct methods means the methods which do not use derivatives, use just the function values. So first, a few general comments about derivative-free methods. They use only function evaluations, quite a few of them, to figure out the appropriate descent directions, and then from the current point, move to a point, preferably along generally along a descent direction to minimize a function. Now, obvious advantages are that derivative evaluation does not have to be done. There is no need to evaluate derivatives, which may be costly. And they rely on only continuity of the function, not differentiability. And therefore you can apply these even for those functions which are not differentiable. Okay. However, there are quite a few disadvantages. Their speed of convergence is typically lower than the derivative-based methods, because derivative-based methods take a far-sighted view of the function and accordingly can move further. Another problem which I find practically very limiting is that sometimes even very close to the actual minimum point, the algorithm doesn't know that it is very close to the actual minimum point. If the method uses derivatives, then first order condition immediately gives an indication that you might have reached the minimum. This feature we have also noticed in the derivative-free methods of single variable optimization, like bisection, then Fibonacci search, golden section search, that unless and until the bracket gets squeezed, it doesn't know that it is actually sitting at the minimum point. Okay. So such a situation is here also, that even after reaching the minimum point, quite often it doesn't know that it is at the minimum point. We will see. Okay. And another issue which is a troublesome factor for theorists, that for many of these derivative-free methods, there is no guarantee of convergence. There is no proof that says that this method, this algorithm operated like this will certainly converge to the minimum. Okay. So that is a problem, that you might end up suddenly someday in a problem where your chosen method does not converge. Okay. So such a thing is possible. However, most of the time, on most of the functions, it does. They typically converge, and therefore they are in wide use because of their advantages. Okay. So now we see some of the methods. Some of them are very simple, very simple. I mean, earliest methods which people designed for optimization, some of them were this kind, derivative free, and they were very simple. And the simplest perhaps is cyclic coordinate search. And it uses almost nothing other than common sense and single variable optimization, line search. Okay, in a way. So in whatever way you do. So the algorithm is disarmingly simple. You keep a tolerance value, epsilon, and take a starting solution, guess solution, initial guess, x naught, and k equal to 0, you start the iterations. To begin with, you evaluate the function at the current point, which is right now xk, which is x0, because k equal to 0 to begin with. Then you do not want to damage this xk, so you leave the xk untouched and put it in y naught. Okay. Now there are n variables. So on y, you operate n times n line searches you do. So starting with y0, see I equal to 1, so yi minus 1 is y0. Starting from y0, you minimize the function with respect to only x1, keeping x2, x3, x4, x5, etc. constant. Okay, so that means you move along the x1 coordinate direction. Okay, keeping everything else as constant. So in other words, you basically conduct a line search along the first coordinate axis, coordinate direction. And as a result, you get y1, the final point of this line search. Then take that y1 and do it for I equal to 2. So that means now keeping x1, x3, x4, x5, x6, etc. constant, you minimize the function with respect to x2, second direction. Okay, and that is that you start from this point. Okay, from y1. Like this, you conduct n line searches. Each time you conduct the line search along one of the coordinate directions, keeping all the other coordinates constant. So after all these n line searches, you arrive somewhere that is yn, and now that you get as the next iterate. If you started from x0, so this yn, after n line searches, wherever you reach, that point becomes x1. Evaluate the function there. I mean, of course, you have already evaluated, you just assign it. And then see whether at x0, the function value you had already, at x1, you have the function value now. So through all these n line searches, whether a significant change has taken place. If the change overall is less than your tolerance, then that means you have converged. So there is no point in going further. So you stop. If that is not within the tolerance, then you increment k, that is you now go for the next iteration. And then again start from here. Okay. So one iteration actually takes n line searches along the n coordinate directions. Okay. So this global convergence is obvious that every iteration function value will decrease only if there is any scope of decrease. Okay. About local convergence, not much can be said because depending upon the function, it might take a lot of time. For that matter, for derivative-free methods, local convergence results are actually lacking. Okay, very scant. Okay, so this was something very simple and not very efficient. Now we will see others. This one, Nelleran Mead's Simplex search. This is also based on heuristics, but a little sophisticated heuristics. And this actually works very well. Okay, so this is quite popular method and it works very well. Though for this also there is no proof, and there are situations where it may not converge. Okay, still most of the time it converges and it does so quite well. Okay, so we will study Nelleran Mead's simplex search method in detail. Now, what is a simplex? That is the first question. You know, in a plane, 2D space, you know a polygon. The corresponding thing in the 3D space is a polyhedron, right? And the corresponding thing in a general n-dimensional space is called a polytope. Now, among polygons in a plane, the one which has the least number of vertices and sides is a triangle, okay, having 3 vertices. In 3D space, the smallest polyhedron that you can think of is tetrahedron, okay, 4 vertices, 3 plus 1. Similarly, a polytope with n plus 1 vertices in ND space is known as a simplex. And what is so special about it? What is so special about triangle in a plane or tetrahedron in 3D space? That they are necessarily convex. If you can define a triangle, that is the 3 points are non-collinear, then the triangle is bound to be convex. Quadrilateral, pentagon, hexagon, on the other hand, don't have to be just by the prescription of the vertices. If I give you the 4 vertices of a quadrilateral on a plane, I'm giving you the vertices. So I might give A, B, C, D in such a manner that C appears in the depressed part of BD rather than on the other side. Okay, so that will not be convex. Triangle will always be convex. Similarly, in 3D space, a tetrahedron will be always convex. And that is the advantage of a simplex in general space. Now, you say a simplex degenerates if all the vertices fall in a hyperplane. Okay, like for a tetrahedron, all the 4 vertices, if you give in a plane, then its volume will be 0. For a triangle, if you give all the 3 vertices which are collinear, then the area will be 0. So these are situations of degeneracy. Okay, so in the simplex search method, you operate with simplices which are non-degenerate. Okay. So how do you initiate the method? Since the algorithm operates with a simplex, so rather than giving one starting point, one initial solution, you have to give an initial simplex, which is non-degenerate. On the way also, all the iterates will have non-degenerate simplices. When the simplex starts getting degenerate, then basically you cannot operate the way it needs because it will then enclose no hypervolume. Okay. So at all the n+1 vertices of the initial simplex, you evaluate the function. Okay. So fine. Now here you might think that, oh my God, giving an n+1 vertex simplex, n+1 points have to generate and ensure that the simplex that gets built out of that is non-degenerate. That is itself a task. No, actually it is not, because it is actually very simple. If you are asked to give a valid set of 3 vertices of a triangle, what you can do? Suppose the 1 point you already have. Then for the remaining 2 points of a triangle, you can go in x direction. Say you have 3, 2 as 1 point in a plane. The second one you can take as 3, 2.1. Third one you can take, 3, 2.1, and the third one you can take 3.1, 2. So these 3 will always be, this policy will always generate a non-degenerate triangle, okay, valid triangle. So from one guess solution, an additional n can be easily framed like this. In each coordinate direction, you move a little from the current one and you get one more. So one you already had, another n you can generate. So developing a non-degenerate simplex to begin with from hand is absolutely nothing. So now we have got how to initiate the method. Now how does it proceed? The rules. During every iteration. Okay. So with the initial simplex, you start an iteration. At the end of it, you will have a new simplex from where you will start another iteration and so on. So during each iteration, there is a scope of these operations: ordering, reflection, expansion, contraction of 2 types: positive, outside the simplex, and negative, inside the simplex, and shrinkage. Now, ordering and reflection, these two will be done in every iteration. And depending upon the reflection results, we will decide what to do out of these. So these are conditional. Okay. So first ordering. First, the vertices are ordered according to the function value and renumbered. I mean, some implementations do not bother to renumber, but just flag this is best, this is worst, and so on. Okay. But more straightforward would be if you renumber. So you renumber the vertices of the simplex such that, this should be fx1. Okay. So that fx0 is least, then fx1, then fx2, this should be fx1. Okay. So functions you order as x0, x1, x2, x3, etc. according to the points you order, point vertices you order according to the function value. Lowest function value vertex is now called x0 and so on. Highest one is xn. Fine. Now, out of all these n plus 1 vertices, 3 of them are of special significance. One is the best, which is x0. The second is the worst, which is xn. And the third is the second worst, xn minus 1. Okay. So best point, the second worst point, and worst point. These three are of special significance. And the task of a particular iteration would be to replace the worst point with something better. Okay. So that is what an iteration attempts to do. And for this task, we will try to move the worst point in the general direction of the other points, which are better. We know. Okay. So lower function value. So for that, if you leave out the worst point, then the rest of the points together will form a face, and that is the best face. Okay. So there are so many faces. Okay. So out of that, that will be the best face, in which the top n of the n plus 1 vertices are lying. So those vertices which lie on the best face, their centroid we find out by this. Sum up their position vectors, divide by n, the number of them. One we have removed. Okay, so that is why n, not n plus 1. Here also you see n minus 1. Okay, the last one is not included. And then the worst point is reflected through this centroid. So centroid plus that much distance on the other side of the worst point. Okay. So xc minus xn is the vector that you have come from xn to reach xc. Now that much you go on the other side also. If you put alpha equal to 1, typically alpha equal to 1 you would put. This would be the usual reflection through a plane mirror. Okay. Now you could put alpha equal to something else, but typically alpha equal to 1 is sensible. Now you would try to move the worst point here. That is a default choice. But you don't have to take the default choice, because you might find something better, or default choice itself may not be very good, okay, depending upon the situation. So to know the scenario at the default choice xr, you evaluate the function here, and following conditions may arise. It can have any value theoretically. So less than x0, between x0 and x1, between x1 and x2, between x2 and x3, and so on. And then finally, between xn minus 1 and xn, or even higher than xn, okay, higher than fxn. So all these things are possible. So all cases we will consider. If the function value is better than, that is less than, even the best point that we have, that means this direction is very good. So we'll have an expansion operation. That is not only till this point, we'll go even beyond. We'll see how. Okay. If the function value at the reflected point xr is between the best point and the best value till now and the second worst value, then it's a reasonable point to go. So in that case, the default choice is taken. So the default choice is taken in the most number of cases, x0 to x1, x0, x1 to x2, x2 to x3, and so on, up to xn minus 2 to xn minus 1. So all this is covered by the reflected point. That is why it is the default choice. Now, if the function value here is worse than the second worst, but better than the really worst, okay, if it falls in the last finite interval, then actually it is not good. Why? Because yes, the function value is better than the worst one, so you could think of replacing the worst point with it. But then you see, the moment the worst point goes out, this newcomer would become the now worst point. And the fellow whom you just now took in, you would like to throw away. So that way, this iteration will not be of great value. So that is why this is not good. So in that case, you say that, well, this direction was perhaps good, but maybe not so far. And then you contract the simplex. Don't go all the way to XR, stay a little inward. I mean, stay a little less, but on this side of the face, on the new side of the face. Now, if it happens that the reflected point has a function value which is even worse than the worst point, that is too bad. That is not even a choice. Nobody can think of it as a choice. So in that case, you don't even go on that side. You pull the worst point towards the best face, but that's it. You don't go on the other side. So that is called negative contraction, because you contract the simplex on the negative side. Don't go forward. So now these expansion, contraction, etc., we will see. First, expansion. We have already discussed the theme of this. If XR is a point better than the current best, then this direction is very good, and we will go even beyond XR. And that means this XE, expansion point, XC plus beta times this, and beta is greater than alpha. Alpha we took 1, so beta will be greater than 1. 1.5, 2, whatever you take. Typically 2 is taken. You can take 1.5 if you are a little conservative. Now, there are two policies here, whether to accept XE. You have got XE with a lot of hope that it will be better even compared to XR. But it may not be so. So one policy is that to replace the worst point, you take XE, whatever. Don't bother what is its value. Second policy is to take XE if here the function value is better than the reflected point. Okay. Otherwise, reflected point you have, take that. So this is the second policy. Now you will be tempted to use this policy, but both policies have their advantages and disadvantages. Mostly, I mean, there are different priorities. This policy expands the size of the simplex. Okay, that is why it is called expansion. So in the initial iterations, it helps you to bring more and more region of the search space under your search quickly. However, the second policy tries to minimize the function quickly. And typically the second policy would be better if you are near the convergence, but initially you don't know. Okay. So both policies have their advantages. So you can choose any one of them and you can experiment which one is operating better for the functions you try with. Okay. Now this is the best case scenario. Bad case scenarios. If the reflected point is in between the worst and the second worst, then XR is not a good candidate for replacing XN, because soon this will be in the line of fire. Okay. So, but this direction is good because compared to the worst point, reflected point is better. This we know. So this direction is better than that direction. From the best phase, from XC in particular, if you look at this direction, that is the reflected point, that is better compared to the direction opposite. So you want to come in this side, but not all the way there, okay? Because then immediately that will be in the line of fire. So you say that not all the way, but a little less. And then rather than alpha equal to 1 here, you put gamma, and gamma is less than 1. So this actually contracts the simplex a little, okay? By this gamma ratio, actually it contracts, okay? And now this new point that you have got, what if the function value there is worse than the reflected point? That would be bad, right? But that rarely happens. But if it happens, then you don't accept it. You accept this point only if the function value here is at least better than the reflected point. It may still be worse than the second worst, but you do not go on trying with gamma. Whatever gamma you have taken, you stick to it, okay? So you accept this contracted point if here the function value is at least better than the reflected point, okay? Otherwise, what to do? We'll talk about it. First, consider the other case also. If the reflected point is worse than the current worst point, then XR is not at all a candidate, and even this direction, this side is also not a good idea. So stay on the other side only, where you were earlier, okay? So we'll just pull the worst point partly towards the best phase and don't cross the best phase, because on the other side of the phase was relatively better, okay? So in that case, the same formula, except that here you have minus. So you come a little backward. So here also the contraction takes place because gamma is less than 1, but it is inward. It is negative side, okay? And again here also, this new point, contracted point, is acceptable if here the function value is at least better than the worst point. Because you are not comparing with reflected point, because you have left that side, you are on the old side only. So you compare with the old side. It has to be better than this for acceptance. If not, then what? In both of these contraction cases, if the typical contraction formula does not succeed, then in both cases, actually in both cases, there are quite a few things common. The new point is closer than the worst point to the rest of the simplex because it is contraction. Typical value of gamma, you take half. And this kind of contraction steps take place mostly when convergence is imminent, and in order to satisfy yourself regarding the accuracy, you need to have the points come together so that the simplex becomes very small within your tolerance. And you see, even if one of your n+1 points is actually the minimum point or extremely close to it, you would not know until your entire simplex comes to that point, okay? Because the minimum point can be anywhere in the simplex. So this is what we were discussing some time back in the beginning of the lecture. So that is why contraction steps are necessary for accurate result, for real convergence, okay? And even the new point that you get XPC or XNC by these two formulae may be unacceptable if the condition is not fulfilled. This condition and this condition, and they are the corresponding condition comparing with XR. In these two cases, if the positive contraction or negative contraction does not succeed, then you apply a shrinkage operation, okay? That is the last operation. So shrinkage operation, you see, is invoked only under conditions when close and interior points of the simplex are better than faraway points, okay? And it typically happens when convergence is imminent. So typical contraction step reduces the size of the simplex, but one vertex at a time. If the normal contraction operations don't succeed, then the control falls here in shrinkage operation. And in shrinkage operation, the reduction of the simplex size is done at wholesale rate. Okay. Not only move just the worst point towards the best face, but move the worst face towards the best point. It is the other way. In the normal operations, we were moving the worst vertex towards the best face. In shrinkage, we move the worst face towards the best point. Okay. That means all the vertices except the best are pulled towards the best point. And that is very simple to do. Okay. Initially, we did not do it because at that time we thought, and at that time compared to the current simplex, the minimum point might be somewhere far away. Okay, but now we know. Okay, so the shrinkage operation is like this. Each of the vertices other than the best is pulled towards the best by this delta ratio. Okay, so delta is typically taken as half. So we have alpha as 1, beta as 2, and gamma delta as half. That is a normal, typical values. So you see, shrinkage operator gets invoked rarely. And why? That's important, because a shrinkage operator will produce n new vertices. That means for the next iteration, you will have to conduct n function evaluations. In the ordinary operations, at every new iteration, you were conducting only one new. Okay, so that is one important thing. Now, see the summary of these simplex methods. Simplex method. So this is a 3D schematic. 4 vertices: x0, x1, x2, x3. This is the best. This is the worst. And the centroid of this point is xc. Okay. Then the reflection operation produces this as xr, and you accept it if the function value is between the function values at x0 and xn minus 1, which in this case x2. Okay. And if it is better, if the function value here is better than even x0, then it is a great direction. And you do not stop here only, you move further. Okay. Here, that is expansion. On the other hand, if the function value at the reflected point is between the function values at x2 and x3, then you say that we want to come on this side, yes, but not so far. Then you contract it here. Okay, positive contraction. On the other hand, if it turns out that the function value at xr is worse than this worst point, then you don't even want to come on this side, you go back to the old side, and then there is a negative contraction. Okay, here, and the simplex becomes smaller. In this case also, the simplex becomes smaller on the other side. If these two processes fail, that in this case here, or in this case here, the function value shows that it is not acceptable. Here it is worse than xr, here it is worse than x3, xn, then you don't accept it. So the failures in these two cases give you the shrinkage opportunity, in which case you pivot x0 and pull all the other three along it, okay, halfway, or 0.6 way, 0.4 way, whatever you decide. So this is the overall plan of the Nelleran-Meads simplex search method. Now this is an iteration. How do you terminate it? When do you terminate it? You need termination condition, and not a termination condition, but there are several. So the termination condition, that is, in an iteration you will go on checking if something, then don't conduct any more iterations. So what if you should check? So you can check based on the function value, or you can check based on the size of the simplex. That is, how close are the x's. If the x1, x2, x0, x1, x2, x3, x4 are all so close that you can say whatever point you take, it doesn't matter. So you take x0, which is the relative best. So, and that's it. So either on function value or on the solution points, or a combination. So convergence based on function value is easy. The worst value, highest value, and the best value, that is the lowest value. If you see the difference as less than the tolerance in function value that you have decided, then you say it's converged. Okay, stop it. Solution space, you have n plus 1 vertices. So you can decide based on how many of them are too close. So you can check their distances and work out whether the condition is fulfilled or not. The best would be if you say that the hypervolume, say, when do you say in 3D space 4 points are very close? If the volume they enclose turns out to be extremely small, then the 4 points must be very close, right? So the same thing here, you try to work out the hypervolume. It's some computation, but not too bad. Okay. So from one of the vertices, if you take the vectors towards each of the others, then you define the sides from one side, one vertex as y1, y2, y3 up to yn. Now, the determinant of these vectors divided by factorial n is the hypervolume. Okay, you can check with area, volume, etc., and it will fit. And actually, you can prove this formula. Okay, that this is the hypervolume. Now, to bring it to the length dimension, you take the nth root, and that should be less than the tolerance value in solution space that you have decided. Okay, so these are the two alternative. I mean, it was not necessary that you talk about hypervolume. You could have decided on some other basis that the points are quite close. Okay, say out of the n plus 1 points, if you find that 5 of them are very close, or n by 2 of them are very close, okay, then you can decide. I mean, it's a little loose, but you can do it. Okay. Now, there is a little issue here. Since in principle, for simplex method, it is possible not to converge. Therefore, you also need to keep a check on how many iterations you have conducted. So you can say that more than 1000 iterations I would not conduct. Okay. Because typically, if it has to converge, it converges within 200, 300 iterations at most, mostly not even that. So more than 1000 iterations I will not undertake under any circumstances. So it is also possible to give an additional alternative termination condition on expiry of maximum number of iterations. That is a standard technique which is used to bring out the program from infinite loop. Okay. So this was Nelleran-Mead's simplex search, which is actually quite sophisticated, though based on heuristics. And it works very well. It has been found very useful, and it is very popular. The MATLAB function fmin search actually uses this. Okay. Now, other direct methods. There are many other methods based on all kinds of considerations. Some of them are very simple, and some of them are not very efficient, not very effective. And these are the earliest methods, apart from cyclic coordinate search. Okay. Simple, without sophisticated theory, and computationally manageable, but not very efficient. One direct method, which is quite efficient and which is actually developed on quite sophisticated theory, is Powell's conjugate direction method, or also called Powell-Smith direction set method. Now, we are not discussing it here because there are other conjugate direction methods, and we will discuss all of them together, okay, at a later stage. Apart from that, modern population-based methods like genetic algorithm, etc., are also actually in the category of direct methods because they don't use derivatives. Okay, but that is not what this discussion is about. Okay, so these are the things which we have done in this lecture. First, we discussed the properties, advantages and disadvantages of direct search methods. They don't use derivatives. They're applicable also on non-differentiable functions. Okay, and they avoid the cost of derivative computation. Nelleran made simplex search method, which we studied in great detail, is quite useful. And I advise you to make an implementation of it for your own practice. Okay? And check that implementation on a few problems of, 2 variables to 6 variables. Then you will get a feel of it. And Powell's conjugate direction method is something which is quite sophisticated, and it competes with gradient based methods, derivative based methods in performance, and we will discuss it later. For the time being, we have postponed it. The next lecture will be on a proper derivative based method, which is the method of steepest descent. Okay, that we take up in the next lecture. For the time being, we stop here. Thank you.